Okay, welcome to Earth and Space Science, Lesson 1, Theory of Plate Tectonics. And as we start this lesson, I just want to solidify our objectives. In other words, what are you expected to be able to do with this information? So the first objective is to define the theory of plate tectonics, also known as plate tectonic theory. And in addition to defining the theory of plate tectonics, I also want you to be able to describe two scientific discoveries that preceded and led to the theory of plate tectonics. And those were the discovery of continental drift and also the discovery of seafloor spreading. And so you should be able to describe those two and also describe how they support the theory of plate tectonics. And so I'm going to assess how you've met the objective based on your Cornell notes and also 5 questions. And the questions are embedded in this lesson, and you'll respond to them in the Cornell notes, and I'll describe how exactly I want you to do that when we get to the questions. But the first thing is our definition of tectonic plate theory. And so I can paste these videos out, and I don't go too quickly. I'll go ahead and write down exactly what I want you to write down. So, not why. What is plate tectonic theory? So that's the essential question. And the answer is, it's a theory that states that pieces of Earth's crust are in constant motion driven by convection in the mantle. So this statement might have some words that you don't know yet. The Earth has layers. 2 of them are the crust and the mantle. And convection is a concept that we'll go into more detail later. But for now, this is your working definition of plate tectonic theory. It's that pieces of the Earth's crust are in constant motion driven by convection in the mantle. And this is a map that shows the Earth's tectonic plates. And the plates are designated by these lines, these boundaries right here. And so each of these boundaries, you'll find some arrows. And the arrows tell you which way the plates are moving. So for example, here we have the Pacific plate, and let's just say the North American plate. So these are 2 different plates. And the arrows right here show you that up along maybe the northern coast or the west coast of North America, maybe Canada, the two plates are moving towards each other, and that's called a convergent boundary. They're moving towards each other. Now, if you go further south along the California coast, maybe the Yucatan Peninsula, down in that area, the two plates aren't moving towards each other, they're not moving away from each other, they're moving past each other. And that's called a transform boundary. So let's look at the Pacific plate and the Nazca plate. Right here, the two plates are moving away from each other. That's called a divergent boundary. So we're going to go into types of plate boundaries in much more detail at a later time, but for right now, you should be able to look at a map like this and know that these lines designate plate boundaries, and the arrows on this map tell you which way the plates are moving. So the first scientific discovery that led to the theory of plate tectonics was continental drift. And continental drift came about from the discovery that at one time, about 200 million years ago, all of the Earth's surface, so all of the continents, were combined into one large supercontinent. And that supercontinent was called Pangaea. And the way that they came up with this idea was they found rock records, geological formations in Africa that matched the properties of geological formations in South America. And the same thing was true in North America and in Europe. And these geological formations, along with fossil records, here you can see they found some along the west coast of Africa and the east coast of South America that matched up, and along the southern tip of Africa and the southeastern coast of South America. Basically, these geological records matched up so perfectly that the scientific community came up with the explanation that at one point all of the continents were connected, and that's what allowed these remarkably similar rock formations on different continents that are now separated by oceans. And so this idea is continental drift. And in your notes, you might say, what is continental drift? That could be your question. And the answer to that question, continental drift, is Earth's continents are moving. And so I'll just go back to show you this illustration of continental drift. Sped up, obviously. This is occurring over hundreds of millions of years. But this shows you that Earth's continents are moving from place to place. Orientation is changing all the time. And this is supported by geological records. So in your notes, to answer the question, what is continental drift? It's the observation that continents are moving. And when I say continents, I'm only talking about land. So the parts of the Earth that are covered up by ocean, that's not included in continental drift. Continental drift is only talking about land masses moving from place to place. And that observation is supported by geological records. In other words, fossil records and rock formations that are found on different continents that are now separated by an ocean. Their presence indicates that at one point those continents were joined and they were all part of one large supercontinent called Pangaea. And so here is a short video that provides a little more detail and perhaps a more thorough explanation of continental drift.
Continental drift. Let's travel back in time and watch continents move. Moving back in time, the Himalayas and Mount Everest disappear as the collision between India and Asia is reversed. Climates are changing. Australia joins Antarctica as India approaches. Going back 150 million years, the continents are joined in 3 large pieces. South America and Africa are on one landmass. India, Australia, and Antarctica form a second. North America, Europe, and Asia make a third. 225 million years ago, the supercontinent Pangaea exists. Let's watch this movement as it occurred going forward in time. As Pangaea splits into 3 large pieces, the Atlantic Ocean starts to form. India starts its race to collide with Asia. As the continents take their current locations, India and Asia collide, and the Himalayas and Mount Everest appear. What is next?
So, there you have it, continental drift. Earth's continents are moving around. And continental drift is not the same thing as plate tectonics. 2 different theories. Continental drift is a piece of evidence that supports the theory of plate tectonics. So when I say they're different, they're not completely different, but there are subtle differences between continental drift and plate tectonics. And so what causes the plates to move? The cause, so for your notes, just write it right underneath here. What causes plates to move? So that should be your question, not this question. What causes plates to move? And this statement is a little wordy, so let's see if we can simplify it. But the statement says the basic machine driving continental movement is heat moving out from the Earth's mantle through the crust and out of the planet. The effect of this is to cause convection or plate movement, So let's break this down. Convection is a scientific phenomenon that occurs when material is heated. It rises. You might have heard the expression heat rises. Well, that's true in all branches of science. And in geology, we consider the internal heat of the Earth. Basically, the Earth is hottest down towards the center at the core. And any material that comes in contact with the core is heated up. And when it's heated up, it rises to the outer more layers of the Earth. And it rises and rises and rises over the course of maybe hundreds of thousands, maybe even millions of years. And it gets to the Earth's surface and it cools down. And when it cools down, it starts to sink back down to the Earth's surface. And once it gets back down towards the middle, it heats up again and it rises again to the top and falls back down once it cools off. And so that process is called convection. And it's that process that causes the tectonic plates to move. And they move very slowly because that's a very slow process. But let's get back to our question. What causes plates to move? Well, convection in the mantle causes plates to move, And just so we're clear, convection hot rises and cool sinks. That's just a very simple summary of the process of convection. And it's that process that causes the tectonic plates on the surface of the Earth to move about. And brings us to question number 1. So, to explain how I want these questions submitted, the first thing I want you to do is in your notes or on a separate sheet of paper, whatever you want to do, write down this statement. The theory that states that pieces of Earth's crust are in constant slow motion driven by movement in the mantle is called A. Theory of continental drift, B. Theory of Pangaea, C. Theory of plate tectonics, or D. Theory of plate boundaries. So I'll go ahead and give you this one. Let's go back to the first slide. The theory that states that pieces of Earth's crust are in constant slow motion driven by convection in the mantle. Tectonic plate theory. Okay, go back to our question. Theory that states that pieces of Earth's crust are in constant slow motion driven by movement in the mantle is called. Correct answer is C. Theory of plate tectonics. So I want you to write the entire statement. The theory, and you can pause the video to do so, blah blah blah. The theory that states that pieces of Earth's crust are in constant slow motion. And then I want you to write the correct answer. The letter too. So C, theory of plate tectonics. And so I'll go through and I'll know what question you're answering and your response. So just to be clear, one more time, I want you to write down this whole statement, and then I want you to write down the correct answer. And not just C, I want you to write down the full statement. Okay, so question number 2. The theory that continents are slowly moving over Earth's surface is called theory of Pangaea, theory of continental drift, theory of plate boundaries, or theory of plate tectonics. So if you need more time to copy down the question and answer, go ahead and pause the video right now and complete that question. Question number 3. What causes tectonic plates to move? Is it A, ocean currents, B, volcanoes, C, the Coriolis effect, or D, convection in the mantle? And I just talked about this one. So again, if you need more time to write the question down, go ahead and pause the video. Otherwise, we're going to move on to seafloor spreading. And seafloor spreading is another scientific discovery that supports the theory of plate tectonics. And the basic idea is that at a region, a plate tectonic region, where two plates are moving apart, like you see here, you see these two arrows pointed in opposite directions. That means this is a plate over here, and here is a different plate over here. And underneath there is magma. And magma is melted rock. And so where those two plates are moving apart, it's called a divergent plate boundary. Divergent means they're moving apart. This one's going this way, and this one's going in the opposite direction. And so, at a divergent plate boundary, there forms a rift. And that rift is a crack in the earth where magma can reach the surface of the earth. And if you can imagine melted rock all of a sudden being placed on the bottom of the ocean, well, it cools down and it forms solid rock. And that solid rock, over time, layers on top of other solid rock, and it creates mountains. And evidence of this can be seen at an area called the Mid-Atlantic Ridge. And the Mid-Atlantic Ridge is this area right here. So this is the Mid-Atlantic Ridge, and there's two tectonic plates moving away from each other. One's going in this direction, one's going in this direction, and the crack in between the two plates is an area where magma is reaching the surface, cooling off, and the plates continue to spread apart, and more magma continues to reach the surface and spread out. And that process, over hundreds of thousands, millions of years, has built up a mountain range in the middle of the Atlantic Ocean called the Mid-Atlantic Ridge. And it's 12,000 miles long. It's a mountain slash volcano range. And here's a video. So I don't want to waste time needlessly. We might skip around a little bit. Let's see. So here's where the geologist is explaining it.
Indicated there was something down there, something big. In 1953, they found out what it was. A 12,000-mile-long mountain range. They called it the Mid-Atlantic Ridge. The reason it's so great. To fill us in, I paid a visit to Neil Driscoll, a geologist at the Scripps Institution of Oceanography.
One of the big discoveries that was made was that there was this ridge of underwater volcanoes that stood high above the seafloor.
How high is a mountain in the middle of the Atlantic?
The average seafloor depths are on the order of about 4,000 to 5,000 meters. The mid-ocean ridge sits up at about 2,500 meters. So they sit about 2.5 kilometers on average higher than the surrounding seafloor that's shown here in the deep blue colors.
So that's over a mile high.
Yes.
And that's where Harry Hess comes back into the story. Analyzing core samples and sonar readings from around the Mid-Atlantic Ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
Harry Hess was in a position that he could bring it all together. Things were spreading apart and new Earth was being generated. But if you did this for long enough, the Earth should grow. And it doesn't.
The Earth doesn't get any bigger.
No. Harry appreciated the fact that if new Earth was being generated in one area, they have to be consumed or recycled in another area.
The process that recycles the crust of the spreading ocean floor back inside the Earth is called subduction. But as our next great discovery revealed, it's all part of a much larger process, perhaps the most powerful force on the face of the Earth.
Okay, so the geologist talked about seafloor spreading, and one thing that was mentioned that's kind of important to note is that all of the stuff that's near the fault line or the plate tectonic boundary, that's new crust. and that new crust pushes old crust out. And so the further away from the plate boundary, the older crust you're going to find. And at this point, that boundary is creating new crust every single day. And so here is a summary of seafloor spreading. And again, let's see. Let's see if we can break it down a little bit. So for your notes, you might say, what is seafloor spreading? And let's see, seafloor spreading happens at the bottom of the ocean at a divergent tectonic plate boundary. The seafloor moves and carries continents with it. At ridges in the middle of the ocean, new oceanic crust is created. So, let's see what the main points are. So, seafloor spreading. Alright. So, the first main point is it happens at a divergent plate boundary. And a plate boundary is an area where two plates interact with each other. You could say they meet, but at a divergent boundary, they're moving away from each other. And yeah, let's move on. So the seafloor moves and carries continents with it. At ridges in the middle of oceans, so this is important, new crust is created. And that new crust is created by the magma that rises to the surface due to convection currents. And it's able to seep through this crack at the plate boundary. And that crack is caused by the two plates moving in opposite directions. And that's seafloor spreading. And so towards the end of the video, they mentioned at other parts of the Earth, the oceanic crust is being consumed. So here it's being created, and at other parts it's being consumed. We'll go into that in more detail at a later date and time. Forgot my question mark up here. Okay, so what is seafloor spreading? There you go. Alright, here are just a summary of how fast seafloor spreading actually occurs. So 10 centimeters a year to 3 centimeters a year on the slow end. And that's about the rate that your fingernails grow, 5 centimeters a year. So New York City and London are getting further and further apart, but they're getting further apart at a rate relatively slow, about 5 centimeters per year. So that pretty much ends our discussion of seafloor spreading. So let's finish the lesson off with 2 more questions. So write question number 4. The process that continually adds new crust is it A, subduction, B, earthquakes, C, seafloor spreading, or D, convection? I'll give you just a second to pause the video if you need more time to write down the question. Question number 5. The mid-ocean ridge, just to remind you, this is the mid-ocean ridge right here. The mid-ocean ridge is in between North America and Europe and the west coast of Africa. The mid-ocean ridge occurs along A. Convergent boundary where new crust is formed. B. Transform boundary where crust is subducted. C. Divergent boundary where seafloor spreading takes place. Or D. Divergent boundary where subduction takes place. And I'll give you just a second. Pause the video if you need to. And finally, summarize today's lesson. So we started off by defining plate tectonic theory. And then we looked at continental drift, and seafloor spreading. And so here, this is our theory, and these two are the evidence that support the theory. Evidence? I think that's how you spell it. Alright, well, either way, that does it for lesson 1.